All right, so today we are jumping into a huge, and I mean huge question. How does science actually work? I'm not talking about in a perfect, sterile lab, but out here in the real, messy world. How do we figure out what's actually true when things get complicated?
Okay, let's get right into it. Think about so many of the studies you see in the news about economics or education or new public policies. You just can't do a perfect experiment for those things, right? You can't randomly give half a country one economic system and the other half another just to see what happens. So, when a perfect experiment is impossible, how do scientists find any answers at all?
Well, this brings us to a really important idea. It's a type of research that honestly underpins so much of what we know about the world, shaping decisions that affect all of us.
It's called quasi-experimentation, and a great way to think about it is, well, it's research out in the wild. You've still got all the main ingredients of an experiment, you've got a treatment, you have a way to measure the outcome, you have groups to study, but you're missing that one crucial magic element, random assignment. You can't just randomly put people into groups.
And this difference you see here, it is absolutely fundamental. In a pure, clean experiment, randomization is the gold standard. It's how you make sure your groups are truly comparable. But the second that's off the table, like in a quasi-experiment, the researcher's own judgment becomes incredibly important. They have to be constantly on guard, thinking about all the other reasons they might be seeing a certain result.
So if a researcher's judgment is that critical, it kind of begs a much bigger, deeper question, right? What is the goal of that judgment? What are scientists even searching for in the first place? What does truth even mean here?
For the longest time, there have been these two competing ideas about what science is. Is it this imaginative, exploratory adventure where big ideas and truth itself kind of take shape inside the creative mind of a scientist? Or is it more of a critical, analytical hunt where the scientist is like a detective and the truth is already out there in nature, just waiting to be uncovered?
But here's the thing. It turns out you don't have to choose. In fact, a great scientist has to be both. You have to be imaginative enough to dream up a bold, new idea. But then you have to be skeptical enough to be your own toughest critic when you go to test it. This beautiful combination is what's known as the hypothetico-deductive model.
Okay, so scientists are these creative critics. Got it. But what happens when you get a bunch of them together? How do they decide, as a community, what's true? Is the whole point to get everyone to agree, or does science actually move forward because of constant argument?
So, one very powerful point of view is that science is all about building consensus. The entire goal is to create this solid body of knowledge, facts, laws, principles, that are so well established that pretty much every expert in the field accepts them as true.
But then you have this completely different idea, made famous by Thomas Kuhn. And he argued that the biggest breakthroughs, the real scientific revolutions, they only happen because smart, rational people are allowed to disagree. Think about it. If everyone always agreed, we'd never have those moments that completely change how we see the world.
This really shows you that central tension perfectly. Is science this steady, calm process of building a wall, brick by brick, on a solid foundation of agreement? Or is it a series of chaotic, revolutionary earthquakes, where old ideas get completely shattered to make room for brand new ones born out of controversy?
To really understand how modern science tries to square this circle, we need to take a quick little trip, a journey through the philosophy of science, which is actually a super fascinating story of how our whole idea of knowing something has changed over time.
You know, throughout the 20th century, the way we think about scientific truth went through some pretty wild shifts. We started with this really strict, rigid view and ended up with something way more nuanced and, honestly, a lot more realistic.
So, it all kicked off with an idea called logical positivism. The positivists, they wanted science to be built on a foundation of pure, absolute certainty. The rule was pretty simple. If you can't directly check a statement with your own eyes through observation, then it's basically meaningless. It was this intense quest for pure objective fact.
But then, this philosopher named Karl Popper came along and just completely flipped the whole thing on its head. He said, wait a minute, you can never actually prove a theory is 100% true. Instead, he argued that a scientist's real job is to try their absolute best to break their own theories, to try to prove them false. A theory is only strong if you can survive every possible attack you throw at it. And just when you thought it was getting clearer, Thomas Kuhn came along and made things even more interesting.
He showed that science doesn't just happen in a vacuum. It operates within these dominant worldviews. He called them paradigms. And these paradigms are so powerful, they're like a pair of glasses that scientists swear, and they're really, really resistant to change. They don't get overturned by one little experiment, but by huge, messy scientific revolutions.
So after all of that debate, going from a search for pure, verifiable facts, to trying to break theories, to understanding the power of these giant worldviews, a much more modern, balanced, and frankly more practical philosophy started to come together.
And this brings us to a modern philosophy called Scientific Realism. It's so cool because it kind of brings all these earlier ideas together. It starts with a simple, common sense idea. There's a real world out there for us to study. But, and this is the absolute key, it accepts that our knowledge of that world will always be imperfect. It'll always be incomplete. And that leads to a really powerful conclusion. Every single claim we make has to be relentlessly, critically tested over and over again.
And that's exactly why scientific realism is so useful. It gives working scientists a practical toolkit. It helps them find that middle ground between the arrogance of thinking you can know everything with perfect certainty and the despair of thinking you can't really know anything at all. It's a humble but also a really rigorous way to move forward.
So, let's bring this all the way back around. How does this big philosophical journey help us with those messy, imperfect, real-world, quasi-experiments that we started this whole thing with? This quote right here from the researcher Thomas Cook, this is the big payoff. He's basically arguing that the perfect mindset a researcher needs to do good work in the messy real world is the mindset of a scientific realist. Okay, those are some big words, so let's break down exactly what he means.
What this boils down to is a really practical way of thinking. First, you have to be a realist. You have to believe there's a real answer out there to be found. But at the same time, you have to be a fallibilist. You have to be humble enough to accept that your knowledge is never going to be perfect. And those two ideas together force you to be incredibly critical, to question every assumption and attack your results from every angle. And finally, you have to be a post-positivist, which just means understanding that facts aren't simple things you just pick up. They're always shaped by our ideas and our tools.
So what's the big takeaway from all this? Well, understanding the philosophy behind the science isn't just for academics. It's a tool that helps all of us become smarter, more critical readers of information. It gives us the power to look past the headline of a new study and ask a much deeper and way more important question. Not just what did they find, but how did they think?